Yeah. It was, but we got something.
I thought you were gonna sit on the chair.
No, I kind of know. Alex was sitting here last week.
Did you get last week's lab video done? Did you get last week's big answers done? Because there were a few questions. And I wasn't sure if you had something.
Last week's lab has I made a video for last week's lab. So you should be able to get all the data from.
Okay.
Hold on. There's extra shares over there, Michael, if you want to share. All right.
I'll do it. They both say Lab 24 on them.
Somebody.
I know. We already pointed that one out. You look at the bottom corner, Drew. It says it on the bottom. It says Lab 24 and Lab 25 on the bottom.
And if somehow.
Okay, well, we're running late, and I hope that Shannon wasn't trying to log in because I realized 5 minutes ago that she might have been. All right, so we're going to talk today about titrations, which is what we did today. We did a back titration. So we're going to talk today about titrations. Oh, I got a hair in my mask. And equilibria. And this was a titration where you had to count the drops, which is really kind of a pain. But you're counting the drops for the sake of trying to come up with the volume. And when you use a burette, that's the way to avoid that, because you can get the exact volume from the burette still going drop by drop. So when you do a titration in a couple weeks, we're going to do another titration and you'll be using the burette, which is kind of the standard. What?
Do we have Spanish or
No Spanish for you. No, there's Spanish for Spanish 2.
Okay.
No Spanish for you. No Spanish for you. So let's see. All right, so neutralization and titrations. We just did this, so this should be pretty familiar with you guys. So neutralization reaction, what happens? What's a rough idea? What you got, Alex?
Acid is added to a base to make it neutral.
Yeah.
Yeah.
So it's when an acid and a base mix, the acid donates protons to the base, and they call that neutralization. 4 different ways this can occur, and it depends on the relative strengths of the acids and the bases. Your final pH in an acid-base reaction, a neutralization reaction, depends upon the strength and weakness of your acids and bases involved. So say you had an equally strong acid and an equally strong base, and you used 2 parts base to 1 part acid. You're going to neutralize, but your final solution will have a higher pH than 7. Yo, Ozzy. Cole, can you figure that out, please? If you have an equally weak acid and an equally weak base, and you mix 3 parts acid and 1 part base, it's still going to be more acidic. It'll neutralize, meaning the acids and the bases will cancel each other out. But if you have excess acid or excess base, and not just strength involved, but volumes too. So as you saw today, you were adding and adding and adding and adding, and it took forever to get to a point where you hit neutral. And that was, we know.
It's Drew making them. Hold them out.
Oh my gosh, I'm gonna strangle somebody. So when you have an acid and a base and they combine, what are the 2 products always going to be? Salt and water, Abby. That's right. So if you have a strong acid and a strong base, the only important ions are the hydrogen, because it's going to make the hydronium, and that's coming from the acid, right? And the hydroxide, which comes from the base. All the others involved are what we call spectator ions. Do you guys remember spectator ions?
Yep.
We talked about them briefly. So you don't need to worry about them. They're just watching. And then your salt and water are always going to be created. So if you look at this example here, you've got your hydronium and your hydroxide, and they're going to always come together and make your water. And then your salt is left over from whatever other ions were involved, because salts are ionic, right? So the reaction proceeds far to the right. This one says, and your pH is 7. And this is strong acid, strong base. And then this is the formula for it, which I don't think you used in any of your problems or anything like that. So And then, oh, those were examples, by the way, at the bottom there. Those were just a couple examples of strong acids. So sometimes these come up in labs. We had a homework question with nitric acid in it, but I don't think we've messed with any of the others yet. So if you have a strong acid and a weak base, your strong acid is going to dissociate completely, because remember, that's how we determine strong acids and strong bases, are those which dissociate into their ions more completely than others. And your product will be your conjugate acid of your weak base, right? This all kind of makes sense. So your net ionic equation involves proton transfer from your strong acid to your weak base. Remember, your acids are always your proton donors and your bases are your what? Proton, your receivers, acceptors, always, always. So here you have your hydronium again, and we're just going to call this base. It's aqueous. And then you're going to end up, whoa, where'd my arrow go? That was fun. That was a slide issue. And again, here's another equation, which again, I don't think we were using for any of these problems yet. And it's in your book. And here are some examples of weak bases. And I don't believe we've used any of these either. So they're not any that you're particularly familiar with. And these are just, so that gives you an idea. So remember, if you have a strong acid and a weak base, and you put them together, what if you have a lot of weak base and only a little bit of your strong acid?
It may even out, it may not.
It may even out and it may not, right? You may end up with more, something that's more basic or more acidic. It's going to depend entirely on the strength of the acid, the strength of the base, and then your volume too. So these are just a couple graphs. I don't think, did your book have graphs like these? I don't remember if it did. But this kind of shows you, yeah, this is, you know, on your y-axis, you have your pH with 7 in the middle there. And on your x-axis, you have your volumes. So this is your strong acid, strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base. And you can just see sort of, you know, right here, you've got a really, it's going to take a fair amount of acid. We have a strong acid and a strong base. So you're adding the acid to the base in this case. It takes a fair amount, and it looks almost like right angles, right? To me, it does at least. And this is strong and strong. And then if you look at this one where it's weak and weak, it's almost a straight line. And for this example, where you have your weak acid and your strong base, it doesn't get all the way to the bottom. And then in this one, it goes very, very low. And it kind of slopes gradually. So titration. So here's what we did today. But today we did back titration and we did it by hand. This is why we use burettes, because by hand is a pain, isn't it?
Yeah.
So Alex, what was your final volume
Final volume
of drops that you used? Or how many? How many drops did you use?
We used 150 HCl and we used 54.
54 sodium hydroxide was what you needed. And you got 54. Sydney, you guys got 120. What was it? How many drops? 120 something.
129.
For her? Yeah, 127, 129, something like that. And Abby, yours was how many? 117. And then Cole, Michael? 96. Okay. So you see there's a fair amount of variation there. Now, some of that, maybe you guys in your group, Alex, just have like big fat hands and you're just squeezing the heck out of the dropper. I mean, that's entirely possible that you were manhandling on the pipette and that's why you had so few. It could also be counting. There's lots of ways. But this is why titrations are so great. It's because we use burettes. So we used burettes last week and you guys saw how that very tall, very thin tube was super granular with the measurements, right? I mean, you could really, really see tiny, tiny portions of milliliters clearly on it. So when you use the burette for titration, you don't have to worry about counting anymore. And it is consistent. The drops are consistent. So it takes away the issue of squeezing too hard, squeezing too light. So what you do is you put a standard solution in the burette. So what's a standard solution? Does anybody remember from your reading?
Is it one with a base and salt and acid?
Mm-mm.
Oh, a solution that has known concentration.
Right. Your standard solution has a known concentration. Okay. So it can be any particular solution. It's typically your acid or your base, and it has to have a very precisely known concentration. So what were the concentrations of the acid and the base we used today? They had the same
1 molar.
concentration.
1 molar.
1 molar. Do you remember what they were last week?
0.1 molar.
Yeah.
0.01 molar.
0.1. They were 0.1. So yeah, so obviously the one we used today was how many times stronger than last week, or more concentrated? Yeah, 10 times more concentrated. So yeah, today that's why I was like, today if you get this on you, it's a little different than last week. Like it's more of a rush to the
10 times
sink.
worse.
Yeah, it's a little more of a rush to the sink to rinse it if you don't have your gloves on or wherever. So then what we put in that burette is our standard solution. And when we are doing a titration, we refer to it as the titrant with a T. Whatever is in the flask at the bottom, we refer to it as a titrand, or to make life easier, an analyte. Because if you have titrant and titrand, you can see how that can get a little confusing. So you have a known concentration in the burette, and then you have an unknown concentration in your Erlenmeyer flask or your conical flask. So why did we use the Erlenmeyer? Why didn't we use a beaker?
Just because it's easier to squirrel.
It's easier to swirl. That's the whole point. So Jules in particular did a great job of nice, even, I got video of the whole thing, is perfectly even little swirl. Actually, it was so perfect and the pattern was so repetitive that it was hard for me not to do this with my phone. When I was you ever do that? Like you see it and you want to just, so anyway, you have your analyte in there and that's your unknown concentration. So titration is an analytical method in which a standard solution is used to determine the concentration of an unknown solution. And then you have this little dude called the equivalence point. So equivalence point is a point at which equal amounts of hydronium, where's the hydronium coming from?
Base.
Nope. Hydronium comes from the acid, and hydroxide, where's that come from?
The base.
That's coming from the base. Remember, anything that ends in hydroxide is a base. You'll hear it, such and such hydroxide, always your base. And you determine that by your indicator color change, which is what we did today. What was our indicator today? Yeah, phenolphthalein, with a heck of a word that nobody likes to say. So yes, so that was our indicator today. It's not the only indicator. I actually have 3 separate indicator solutions, no, 4, sorry, separate indicator solutions upstairs plus litmus paper. All right, and then also, if you don't have an indicator, there's other ways to monitor it, like electrodes and pH
What are they
meters.
called? The electric ones?
The pH meter, just the electronic kind, the electrodes. So you get a dramatic change in your pH at that point. So as I said before, your titrant or your analyte, that's the substance. And it says here, such as a reagent solution of precisely known, oh no, titrant, not titrant. Yep. So added. So titrant, see, that's what I'm saying. Your titrant here. And you'll see the word reagent a lot. And reagent is pretty much always referring to something on the reactant side. And you'll,
Which is the right side of the equation.
correct. And you'll, no, the left side.
Oh.
Left.
What? Oh yeah, reaction.
Left,
Yeah.
right. Yeah, I have to do hands. Yep. And then your standard solution, as we said before, is precisely known concentration. What are the ways that concentration can be denoted? Do you guys remember?
Molar.
Molarity. Yep. And then you could also do, so we use molarity because remember, if you did milliliters of solute to total milliliters of solution, you could also do milliliters of solute to milliliters of solvent. You could do grams of solute to milliliters of solvent, right? There's lots of ways to denote concentration, but molarity is going to be the most accurate every time. So we try to stick with molarity whenever we can. So now here's the thing about indicators. You have to choose the right one. And the reason you have to choose the right one is because they all have what's known as a transition range.
Yeah.
And you need to match that endpoint pH as closely as possible in order to minimize your titration error. So what's that mean? So say you have this methyl violet, which is the one on the far left.
Whoa.
Can you think of what you might use that for? Like,
If you put it on something and it's not purple, you don't want to touch that thing.
there's that.
It's a safety thing.
There's
You
that.
just kind of throw it in a room. If there's ever a spot that's not purple, you have to leave the room.
But what if it's 14?
You're on top of
It's still
that.
purple.
Yeah, but that's super, super basic. That's bad too for you. So say you have a bathtub full of concentrated hydrochloric acid and you want to add you want to add your base to it
First, how did
by,
we end up with a bathtub hydrochloric
I
acid?
don't know,
How did that?
I don't know.
How
You,
did we?
you have some kind of
How did we get
crazy
that?
gig on the side. Crazy gig on the side. You have a bathtub, let's see, how many liters is our bathtub? Who wants to pick a liter? 50 liters. It's a kind of a smaller, 50-liter bathtub is kind of small. It's like a, whatever.
It's like a sink.
Yeah, you're in your 50-liter tub, and now you are gonna add your base to it by the milliliter. This would be a great one for you to use. Do you see why?
Yeah.
Because that change is gonna occur way, way, way down there on the pH scale, like just a little over 1. So when you slightly, it gets even just slightly basic, it's gonna bling, right? And then, so some of these you see have a really wide range, and some of them are like a consistent range, like the litmus, for example. You can see that has a color the whole time. It just kind of is a shade, it's a shade of pink, a shade of purple, a shade of blue. Whereas some of them have no color and then color, like the phenolphthalein we use today. So you can see that when it's pointed out for you there. And it doesn't change, if you note, until about 8.3. So you actually neutralized your solution before you knew that you neutralized it. By the time you saw it, it was slightly basic already.
Yeah.
Close to neutral, pretty close.
Close
But
enough that it's not gonna hurt.
yeah, slightly basic already. So I have, what do I have? I have methyl orange, I have bromophil blue, and I have phenolphthalein, and I also have universal indicator upstairs, which kind of does a shade from 0 to 14, which is really kind of fun. So if you're carrying out a titration, there's a great WikiHow, no joke. WikiHow can be ridiculous. There is a fabulous WikiHow on how to do a titration, and it is a step-by-step. So, for example, today, prior to you getting a hold of your glassware, I prepped all of it, which means I cleaned it all, I rinsed it all with distilled water. Like all of that is part of the process, and it has to be, right? Because you don't want any remnants on there of some other chemical that could mess up your entire titration, because some of it's really, really granular, really granular. Like one drop makes a big difference, and you saw how much a drop was. What was someone's average volume per drop? Okay, yeah, most people
0.04.
0.04. Yeah, it should be like 0 point something around, a little less than 5 probably. So they're itty bitty. So that tiny volume changes. That's yeah. So that's why all those steps with rinsing everything and whatnot matters greatly. And there's a good WikiHow on it. Also, when you're using a burette, you guys probably saw in your reading about making sure there's no bubbles in it. Because if there's bubbles in it, it'll totally throw everything. I had one last week that had a bubble down in the nozzle, and I kept running distilled water through it, trying to get it out, and it wouldn't go out. It was making me insane. So a lot of the time what people will do is they'll get the water in the nozzle of the pipette. They'll get it down so there's just a little bit of water, and then they'll add their chemical on top, and then just rinse it, keep it open, and then close it. That way you're sure you have no bubble and you only have the standard solution you want. So you have to select your suitable indicator. So here's where we talk about transition range. Indicators do not change color precisely at 1 pH value. They change over a specific range of color, and they continuously change. The range is different for each indicator. The transition point of an indicator is defined as the point at which the acid and alkaline forms of the indicator exist in equal concentrations. So your end point is the point during a titration when an indicator shows that the amount of reactant necessary for a complete reaction has been added to the solution. And then here's your end point and your equivalence point, because they're a little confusing. So the main difference between the equivalence point and the end point is that the equivalence point is a point where the chemical reaction comes to an end, while the end point is the point where the color change occurs in a system. Okay, so your equivalence point is when it comes to an end. When did today's reaction come to an end on the pH scale?
8.5.
Well, that's when we
8.
saw it.
Yeah.
8.3. Well, when did it actually end? When was the neutralization actually done?
7.
At 7, right? So your end point is where it ends. Your equivalence point is where you have equal amounts of your acid and base. So what you're looking for here really is that, see again, it's like your equivalence point and your end point are not quite the same thing. Your equivalence point is where your chemical reaction comes to an end, and your end point is where the color change occurs. So here's your end point, your color change occurs. Your equivalence point means you have hydronium and hydroxide in equal amounts, which means you have a pH of 7, right? So end point, color change, equivalence point is when they're equal.
Will the equivalence point always be 7? How, when would it be different?
It should be, but not necessarily, because when we were talking before about strong acids and weak acids, and so sometimes what you might get is you've reached a point where your all the hydronium that's in there and all the hydroxide that's in there that can react have reacted, but it's still slightly basic, or still because you used a strong acid and a weak base, or your volumes were off, different. I'm not gonna expect you guys to get too nitpicky with that stuff. So titration, concentration from volume to amount in moles. All right, so here is one of your, was this a homework question? I'm trying to remember. I think it might have been.
It takes 35.
Yeah, so it
It's
takes
similar to the
83, yeah, similar. Okay, so it takes 83 milliliters of 0.45 molar sodium hydroxide to neutralize 235 milliliters of hydrochloric acid solution. What's the concentration of the hydrochloric acid solution? Okay, so what do we do here?
We need the equation for
Yep.
Ka.
All right. Or you can use this here. You've got moles of your acid times volume of your acid should equal moles of your base times volume of your base.
That's not what we use.
Okay, well, did you get something similar? So here you have, oh, sorry, my nose is itching today. So we have hydrochloric acid, sodium hydroxide, and we can note when we come down here, it says note Na and Nb are the number of moles from the balanced equation. So this is an easy one to balance, right? We don't have to add any coefficients. Remember, because we did the same reaction last week, right? We don't have to add any coefficients to this.
Yeah.
So you come in here and you're going to put in your moles of your sodium hydroxide. Your moles of your sodium hydroxide times your volume, and that's over your volume of your acid. And your one here this is molarity, and this is your number of moles, 1 and 1. Your number of moles are your coefficients, 1 and 1. Remember last week's lab where we had, okay, remember who watched the video from last week's lab? Did anybody watch the video to try and get answers? You did? Anybody else watch it? Okay. So when you got to the part about coefficients in the end, can anybody kind of explain how that related to the number, how that related to the volume of base needed to neutralize the acids based on with the coefficients involved?
I don't understand the
I
question.
remember you kept saying, look at the coefficients
Yes.
in the video. I don't remember exactly how they did, but I remember that they were involved.
Okay, so let me show,
Yeah.
because I have that on a slide too, which is probably
I
easier to
didn't
see.
really understand how you got the final answer.
Yeah, I was afraid we were hidden there.
Yep.
So let me show you.
All the answers we were able to do, except for the final.
There's Shannon.
That didn't add up. Hi, Sharon.
Hey Shannon, if you tried to come in earlier and we weren't here, I apologize. Lab ran a bit late. All right, so here's the slideshow with the group data from last week. We're just talking about last week's lab for a minute. We're trying to relate something. Okay, where did we get it all in here? I'm gonna get to the one where we had all the data. All right, so here were all of our averages, right? Everybody gets that.
Mhm.
All right, where is
We
this?
got this.
Got this far. Everybody got this far. So then what we did is we got our average numbers, which was easy because we'd already kind of done that when we
Yeah.
made this chart. Okay, skip along, slideshow, skip along. There we go. All right, so here's where people were getting lost, right? So compare your responses to
Oh,
analysis,
no, we
or
didn't.
in analysis item 1. Was there a difference in the number of drops? So here's what we were to be looking at. So our drops here was our volume and our average, and looking here to see if there are any coefficients, but we didn't quite even get to that point yet. So we had 2 milliliters to 20.4, and then we had 4 milliliters to 43.4. So those were our ratios. And then at the bottom, when we get to that one, oh, forgot this came in. So your number of drops doubled when your volume doubled. That makes sense, right? Of course. This part made sense. It was when we got to the next step that people really started to get lost. So have a look at that. It's going to ask us now to look at the data we got from the first trial and compare it to the second trial with a different acid.
Yeah.
So here is what we found. We had 2 to 57.2, right? So the number of drops almost 3 times greater. So what was going on? So if I put it all out here, you can see, so what I did here is I broke it down. Yes, sir.
You said, oh, yeah.
You good? All right. So I broke it down here to a 1 to something ratio. So does everybody see how I did that? We had 2 to 20.4, which is 1 to 10.2, 4 to 43.2, 43.4. So I broke it down just
Yeah.
so you can have a better, it's easier to see, right? It's easier to see the change if you're dealing with 1 in your ratio. So it took here between 10 to 11 drops of the sodium hydroxide to consume the hydrochloric acid, right? And then in this case, it took, I tapped you. There you go. 29 drops to consume the hydrochloric acid. So change those, put those in. All right. Yes.
A brownie code. You go back.
No, you might have, but let me keep going so we don't run out of time. We'll go back if we have time, unless it was a calculation, was it?
You said it was the 57.2
Mm,
or whatever it was. You
Yeah.
said that was also hydrochloric acid, but it wasn't.
no, that was sulfuric.
But you said it was hydrochloric acid.
Just say it or
Hydrochloric
just say it on
acid
the board?
popped up.
Where?
Back one more.
Back one more. Mm. Here.
Yeah, look.
Oh, yeah, that's a typo. You're right.
Yeah. Okay.
No, I said it was, yeah, you're right. That's a typo. Okay, there you go. Well, not a calculation thing. So I also spent probably 48 hours on this lab because it jacked up. Every time I did it, I would transpose some number wrong to a different page and then everything went wrong. So here's where the coefficients come in. All right. So what's your coefficient for your hydrochloric acid? It's 1. Even if you don't see it, it's 1, right? What's your coefficient for your sodium hydroxide? It's 1.
One.
You got a 1 here. And what do you have here? Ding-a-ling-a-ling, we have a 2. Okay, so what's up with the 2? So look at these ratios again. Your coefficient ratio is 1 to 1, right? Your volume ratio is 1 to 10.5. Everybody understands that?
Yeah, my ATI.
Yes?
Yeah.
Are you sure? Over here, you got it? Sydney, you got it? You know where this came from? This was the drops, remember? For every milliliter of hydrochloric acid, it took 10.5 drops of sodium hydroxide. All right. Then here you had coefficients were what? 1 to 2, and the volumes were 1 to 28.6. All right, so here's where, all right, so the factor, how do I explain this one? So the factor by which these ratios differ can be used to kind of compare your data, which is what analysis 4 was asking, the one that everybody was like, huh? So if you go from 1 to 1, you multiply by 1, right? And if you go from 1 to 10.5, you're multiplying by 10.5. And in this case, it's 1 to 2, so you multiply by 2. And this is 1 to 28.6. So something, these are not the same. The factor by which they differ isn't the same. So a separate amount, maybe you can see it a little better. Yep. All right, there we go. There's that one.
Yeah.
So why is it 14.3? Because it's
half of 28.
half of it, right? So if we're comparing 1,
Yeah.
so why is one 10.5 and the other 14.3? Okay. Look at these two, and now you have to try to look at your data and say, well, what can I learn? So if this is correct, all right, if you're using your data from this trial with the hydrochloric acid, if that data is correct, it should take, I lost my spot when I was reading. So using the data from the hydrochloric acid trials, which showed our ratio of NaOH coefficient in this chemical equation is 1 to the volume of drops differ by a factor of 10.5. We should expect our volume of sodium hydroxide here to be around 21 drops, because if it's 10.5, if it takes 10.5 hydroxide, drops worth of hydroxide to neutralize this hydronium, then you should expect this to also be 10.1. And if this was 10.1, then we wouldn't see 28.6, we would see 21 because your coefficient's 2. Okay, yeah.
I'm guessing it's off because different sizes of drops.
Yeah,
some
there's
is
lots of
off.
ways it can get off, lots of ways. So if you're seeing this is 10.5, if you use your data from the first one to extrapolate, then you should expect this one to become 21. And if you use your data from here to extrapolate, what should this one be? Not 10.5, but what?
14.2.
14.3. So one of these is wrong, or both of these are wrong. Likely, they're both a little wrong because we were doing a lot of manual stuff, right? So when you're doing a lot of manual stuff, there's a lot of room for error. So this could actually be anywhere from 10.5 to 14.3. It could be in this range. Does that make sense?
Yep.
Same thing here. This one's going to be in a range too. What's it going to be in a range of?
21 to 28.6.
Yeah, there you go. 21 to 28.6. So if you want to know what the average is, like, say we are somewhere in this range, we got 12.4. And if we're somewhere in,
12.4 is the average between 10.5 and 28.6.
it's the average of 10.5 and 14.3, 12.4.
Okay.
Okay, that's right in the middle. All right, the mean, really. So that's, or median actually.
Well, that one's average.
No,
Okay, so
mean.
21.
Yep. So right here. And then here, if you look right here, your average of your 21 and 28 is 24.8. Okay. What are we noticing? 12.4, 24.8. It's double. Yeah. And what else is double? The coefficient.
Is it?
Yeah. Look, 1 and 2.
Oh, yeah.
So 12.4 to 1 is probably pretty darn accurate, right? Really close. So if the coefficient, the actual factor by which the coefficients and volumes differ is likely between 10.4 and 14.5, your new average is 12.4.
So to get a reaction for every 1 liter or 1 milliliter of ACI, it takes 12.4 drops of NaOH for the reaction to occur.
Yes, that's what you
I
should
found
expect.
Another brownie point.
Oh God,
It
what?
says it differs between 12 and 28.6.
12.4. Yeah, there you go.
And it shouldn't even be that.
No, it should be 21. That's what this is. It's a transposition. Yep. That should be 21. I just typed them in reverse order. So you got 1 to 12.4, right? You see it right here?
Mhm.
And you got 2 to 24.8, which is the same thing, right? So our results are off a bit. Ratio we expected to see in procedure 3 should have reflected the relationship between sodium hydroxide coefficient and the volume of drops of sodium hydroxide required to consume the acid were proportional to the ratios we observed in 1 and 2. Coefficients in the balanced equation were at a ratio of 1 and 2. And the same volumes of acid were used, but different amounts of base were used. With the inclusion of all the class data and all the averaging, you're able to see that your ratio is pretty close. So you can take that same thing, the 12.4, right? And it's asking you here, how much sodium hydroxide would you need to react completely with a 2 milliliter sample of nitric acid? So all we need to know is the coefficient, and it's still 1 to 1. So if you need 12.4 drops of sodium hydroxide for a 1 milliliter sample of acid with a coefficient that's 1, then you have to think to yourself, well, can you really put 12.4 drops into anything?
No.
How you gonna do that? You can't. So if you're doing drops,
You could, but you'd probably need it.
yeah, you'd need a burette, which we're not using. We're using a dropper. So you could have to say 13 drops, and then it's going to be between 25 and 26
Jack, Subway.
Oh, hey, no. Ozzy, no.
because you're wanting to do 2 milliliters, so we got to go back to doubling the volume. So it should be around 25 or 26 drops. So hopefully that, does that clear it up a tiny bit even?
Yeah.
A little bit? Okay. Oh, because this isn't, go to the button. Beep, 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 beep. Oh, wait.
Is there any food left in it, or is it just?
No, it's the bag. So here is where those coefficients play in, 1 and 1, because it says they're your number, they're right here, where it's 1, 1, 1, 1, totally one all the way across.
There's no hand there.
All right, so equilibria of weak acids and bases. The strength of an acid can be measured by the fraction of the acid molecules that undergoes ionization or loses a proton. Remember that the stronger acids dissociate more completely, there's not a word for more completely, than weak acids do, right? So it's a fraction, it's a portion of the whole that is going to ionize and make it stronger. So strong acids are those that ionize completely in water. They give up their protons completely. Strong acids are better proton donors. And so some of your acids are going to be better proton donors, and some of your bases are going to be better proton acceptors. So here are examples of strong acids. So we've used hydrochloric in here, and we did a problem with nitric, but we haven't used any of the others, I don't think.
Sulfuric.
So, oh, we did use sulfuric. Yep, you're right. Didn't even see it there. We used both of those last week. Some bases are going to accept more protons more readily than others. So they, again, are going to be the ones that dissociate more completely. When they do that, they give up their hydroxides. So the thing you guys need to really nail into your heads where acids and bases are concerned is where they fall on the pH scale, which is pretty easy. That's an easy thing to remember. That your acids donate hydrogens, which are your protons. It's an H plus. But in a solution, in an aqueous solution, what are those H pluses going to come in contact with? In an aqueous solution,
OOHs.
H2Os,
Yeah.
right? And they're going to form H3O plus, which is your hydronium. So associate your acids with both your proton slash hydrogen slash becomes hydronium in aqueous solution. Keep that together for acids in your head. And then for bases, they dissociate and they end up being what? What do they dissociate? What's the ion that we care about with bases?
OH.
The hydroxide, right? Your OH negative. So you have your H3O pluses and your OH negatives. And what happens?
Together they make water.
There you go. When you put your acid and base together, you always end up with water and
Salt.
salt. And the salt comes from the conjugate part of the acid and base, remember?
So the stuff that's not oxygen or hydrogen.
Right, the ions that are, the ions that are not the oxygen or the, that are not that don't become the hydrogen and the hydroxide, because there may be some other oxygens in there that are, if you get super involved. So here are your strong bases. So you've got some sodium hydroxide, which we've used. I don't think we've used any of the others, but there they are. So here's a chart, relative strengths of acids and their conjugate bases. So this is just interesting. You've got your hydrochloric acid here. They're putting that in your strongest category, right? And your chloride ion itself is pretty weak. And then you've got your sulfuric acid, hydrogen sulfate ion. So you can see that your weakest bases and acids, when together, their ions by themselves, they're denoting those as stronger or weaker, and it's opposite. Just to see. So this dude here, I like this dude. He talks about acid dissociation constants. He's not Professor Dave. He didn't have a great one, but this guy does. So acid dissociation constant, wait.
This one you're gonna learn about.
No, wait.
acid and base
Wait.
dissociation.
Professor Dave would have known.
I know, Professor Dave would not have interrupted. So your acid ionization constant, this is this Ka. Did you guys see this in the book?
Yep.
All right. And then there's a funky looking formula that goes with Ka. And did you see this ice bit? Has anybody seen this before?
Last week.
Okay. Last week.
Last Friday I saw it.
Last Friday. So here we go. Let's see what he has to tell you. He's going to explain this. This
one
is
you're
part
gonna
of
learn
setting
about
up the
acid and
equation.
Base dissociation constants. First, we'll learn the difference between a strong and weak acid and base. Then we'll learn how to write a dissociation constant expression. And then finally, we'll solve a sample problem in order to use those dissociation expressions. So first, the difference between a strong and weak acid. When an acid or a base, we could also say a base, dissociates or dissolves in water, it's going to split apart. And for acids, they're going to split into hydrogen ions and then some kind of anions, the negative charge. And so hydrogen ions have a positive charge. If an acid or a base is going to be strong, it means it's going to dissociate 100% or completely. So for an acid, we would have all of our acid molecules here put into water, and as they dissolve, they would all split apart, and we get all these free ions floating around in the solution. And so that gives us 100% of these acid H plus ions, which makes an acid. For a weak acid or base, only some of those particles are going to split apart. So with our weak acid, maybe only one of these will actually split, whereas all the rest will stay together. And so we don't get as many of these H plus ions as the strong acid. With a base, we're not concerned with H plus, but we're concerned with hydroxide, this ion right here. This is what makes a base a base. And usually we have some kind of metal. This is sodium that's attached to that hydroxide. And so when it dissolves, it dissociates. We're going to end up with the metal ion, which doesn't really do anything as far as making something acidic or basic. And then we have the hydroxide. And so the more hydroxide ions we could get into solution, the stronger the base is going to be. So we can determine how strong or weak an acid or base is by calculating the dissociation constant. Now, the smaller the dissociation constant, the weaker the acid or base is going to be. The dissociation constants are going to be based on the way that these substances are going to split apart or dissolve. So we'll start with this one. This is hydrochloric acid, which is a strong acid. When it breaks apart, we're going to end up with the hydrogen splitting apart from the chlorine. And so we'll get this kind of thing in solution. So the dissociation expression is going to compare the amount of stuff that split apart to the amount of stuff that remained whole. And for an acid, we use the symbol K sub A, and this is the dissociation constant for an acid. And what we do is we take the concentration of the two products, that's these things over here. Generally, it's always going to be H plus and some anion. So we'll take the concentration of the hydrogen ion times the concentration of the anion, and then we divide that by the concentration of the reactant, which is the thing that we started with. So we're comparing how much of this stuff split apart, this stuff over here, to how much remains.
Can you tell me to stop, please?
And so the bigger this
Just tell
number,
him. Just
and the
please.
biggest we would get is 1, but the bigger this number, the stronger the acid is going to be. Here's another example below this, and this is called acetic acid.
That's
A
vinegar.
little bit different
Yeah.
looking, but it works the same way. We're just going to take off one of these hydrogens. This is a weak acid, so it will not dissociate completely. And we'll end up with the anion here and a hydrogen ion. And to write the dissociation expression, we would take these products and divide by the reactants. And then finally, we have a base. And in this base, we have a sodium and a hydroxide. They're going to split apart, and we'll end up with the sodium metal and a hydroxide ion. And since we're
So is
the base this time, we're going to use the symbol K sub B. And we'll do the same thing where we take the products. That's going to be a concentration of sodium compared to the concentration of hydroxide. And divide that by the concentration of the thing that we started with. So let's go ahead and try calculating one of these constants. So this problem says a 0.1 molar solution of acetic acid has a hydrogen ion concentration of 1.32 times 10 to the negative 3 molar. And it says, what is the acid dissociation constant? The first thing you want to do when you're solving a problem like this is write out the dissociation chemical reaction. So this is acetic acid. That's the chemical formula for acetic acid. And this is going to dissociate into H plus, and the anion like that. So we'll start with that. And what we want to do is we want to look at the initial concentration of acetic acid, what we started with. That's going to be this amount right here. So we started with 0.1 molar solution. And so this represents before this thing is dissociated at all. So this is our initial, that's what I stands for.
Here's your ice.
And these are both
ICE.
going to be 0 because nothing's split apart yet. Next, we'll look at the change, how this is going to change. We'll represent that by a C. And the hydrogen ion concentration is going to change from 0 to 1.32 times 10 to the negative 3. Now, based on this chemical reaction, the stoichiometry here, it's a 1 to 1 to 1 ratio. And that's looking at the coefficients in front. If there's nothing there, that just means there's one of those substances. So if this goes up, it's increasing by 1.32 times 10 to the negative 3. This has to go up by the same amount because it's a 1 to 1 ratio. Now, since this stuff is splitting apart, the acetic acid is splitting apart to form this, every time one of these splits apart, this is going to go up, which means this has to decrease. So as these go up by 1.32 times 10 to the negative 3, this must decrease by the same amount. Again, it's a 1 to 1 to 1 ratio.
That makes sense right there, what
So
he
we
just
have
said?
These parts
Kind
going
of,
up,
but
I
why
can see
does it
a
have
plus,
to-
and then
Okay, so did you get that? So what he's, what?
Finally-
Shut up.
Whoop.
So what he's saying is your ratio is 1 for your whole,
Yeah.
and 1 and 1 for your
Yeah.
parts.
Why
So
would you have to minus if the first solution is the first substance just completely disappears?
why would you have, oh, right here?
Yeah.
Because he's just noting in his chart the change.
Okay.
So right here, you see that it disappears,
Yeah.
right? Okay, that's what he's just noting it there.
how does it change or what's the result? We call this the equilibrium. And so this is commonly called an ice chart, the thing that we're creating here. So it's the initial amounts, the change, and then the equilibrium. All we do is we look at each column and we just do the math here. So we'd have 0.1 minus 1.32 times 10 to the negative 3. And over here, we're just adding that amount. Now, when we plug in the information into our equilibrium expression, it's the amounts at equilibrium that we're concerned with. So we always have to start with this given information and then decide how much is everything going to change by. The equilibrium expression for this is going to be the concentrations of hydrogen times the concentrations of this anion over the concentration of the original acetic acid.
Okay.
And now,
So that's the H and the HA right here, hydrogen anion, hydrogen
information
anion.
from our
So I
chart,
know how to do it now, but I didn't do it.
and we
Yeah.
solve for the Ka.
That's fine, you're good.
And I end up with a Ka that's going to be equal to 1.77 times 10 to the negative 5. And so there's my acid association.
And he has a
constant for
Patreon, I
acetic
guess.
acid. And because it's a really small number, I know that acetic acid is going to be a weak acid and it's not going to dissociate very well. And so that is acid-base dissociation constants.
That hopefully makes a bit more sense. So when we look back at this, no, wait, not looking back, looking forward. Go forward, little dude. Wrong way.
This would
No. So I've got this here for you. These are done. These are ionization constants for particular acids, so and particular bases. Just gives you an idea of where the numbers lie, so you can tell what's strong and what's weak based on the size of the number.
So the bigger the number,
Mm-hmm.
the stronger?
Yes. So for example, so here's your hydronium ion. And it's got a 1.0 because you can't get any stronger than that, right? And
Yeah.
here is your hydroxide ion. And all these other numbers they're negative, right? So they're all smaller than the 1.
Yeah.
Cool. All right, so buffer solutions. So what's a buffer solution? Anybody remember?
Yeah. I wrote it down.
I wrote that down, yeah.
Mhm.
A solution made from a weak acid and conjugate base that neutralizes small amounts of acids or bases added to it.
Right. So you use buffers a lot in biology labs. Sometimes you'll use them. The purpose of them is usually it's to maintain a pH, to not allow it to flux too much. So it resists pH change when you add acidic or basic components. And it's able to neutralize, as you just said, small amounts of acid or base. So you're remaining, it maintains a pH in a relatively stable situation. And it's important for processes or reactions that require specific and stable pH ranges. Has a working pH range and capacity which can dictate how much our acid and base can be neutralized before pH changes and the amount by which it will change. What did I type wrong now? Did you put your
I'm
hand up?
not sure if dictate should have an S on the end. It should be dictate or dictates.
Nope, it's plural. Range and capacity,
No, that can work. That works.
two subjects.
That's what I was
Has a
thinking.
Which
working pH
dictate.
and capacity.
Yep.
Dictate, yeah, no, you could say which dictate.
Yeah, that's right.
Which dictate, which.
Yeah, range and capacity, two
I
things.
really like that.
Yeah, he really does. So buffers have two ingredients. An aqueous solution containing a weak acid and a conjugate base.
So cut him off the brine and-
And an aqueous solution containing a weak, a weak base and its conjugate acid. So it's one or the other. Okay? And I'm gonna show you guys this, so they stabilize pH. This is another good video. I'm gonna walk off
In
for
this
1 second.
online lecture, we're going to
He's loud.
discuss buffer solutions. And
This
what
is
we wanna
quick. It's
know
the
about a
3-minute
buffer
one.
here is
Just
that
to wake you guys
first
up.
they resist changes
Yeah.
in pH.
That'll do it.
We're going to see two buffers are made up of a weak acid and its conjugate base most of the time. You can also make up a buffer by a weak base and its conjugate acid. We're also going to see three, how the buffer resists changes in pH. It does it by the weak acid consuming any hydroxide ion added to the solution, and the conjugate base consumes any hydronium ion added to the solution. So let me show you how that works here. Let's say you have a solution that has a buffer. Here's our weak acid HA, and here's his conjugate base A minus. Now, how is it that this species resists changes in pH? Well, remember, one way to change the pH is add a strong acid or pure H plus into the solution. Let me show you what happens here. After this is added in here, then the A minus combines with that H plus, and think about it. The A minus is attracted to the H plus, and what happens is it comes together and makes HA, which notice happens to be our weak acid of our buffer. But the key point is think about it this way. The A minus is almost like vacuuming up all the H plus that's
What?
and converting it into HA, therefore removing H plus from the solution. Now, remember, that's not the only way to change the pH of a solution. You could also add a strong base or pure OH minus. In this case, it's the HA of the buffer that takes care of the OH minus. Since he's a weak acid, what he does is simply protonate the oxygen of the OH, turning that into water, and as a side product, we're also getting A minus. In this case, HA is vacuuming up all the OH minus that gets added to the solution, therefore removing OH from the solution. This in turn means that the pH will remain constant for this solution. Now, keep in mind, buffers have a limit. It depends upon how much HA and A you have in solution.
Yeah.
For instance, if I keep adding a bunch of H plus and I run out of A minus to combine with it, then at that point you have exhausted your buffer and the pH will now start to change. So what have we learned here about buffers? Key point number one, that they resist
point number one.
changes in pH.
Goofy little voice.
And number two, they're made up of a weak acid and its conjugate base,
Hmm?
or it works just as well with a weak base and its conjugate acid. And we also saw how they resist the change in pH, and that is the weak acid consumes any hydroxide ion added to the solution, and the conjugate base consumes any hydronium ion added to the solution.
Yes.
There is a brownie point.
Okay, what?
Upon the additions of an acidic or basic components.
Where are you looking?
Top. It's the
One.
very first dash.
What?
Upon the
He's saying it
addition
should be
of an
A
acidic
instead of
or
A
basic.
N.
Component. Okay, yeah. All right, that's 3 for you today.
What? How do you know if it's supposed to be N or N or A?
No, it should have said component, not components. It could have said acidic or basic components or acidic or basic component.
Every week. And
Yeah.
then he says no.
Okay.
All right, so buffer solutions. A little more on buffer solutions. Buffers are all around. You don't realize it, but they're part of your normal life. Without them, you would not be alive. So there's buffers in your body. So buffers are used to keep the bloodstream at about 7.4 pH level. Specifically, it's carbonic acid and hydrogen carbonate. If you didn't have buffers keeping your blood at 7.4, you'd end up with like acidosis or something terrible like that, and you would be in bad shape.
Does it have to be? It's like is it depending on your diet? It might go up to like 7.5 or anything?
Not really.
You just want it to stay at 4 constantly.
Mm-hmm.
So it's not like blood sugar where it can go up or down.
That's a little different, yeah. Mm-hmm. So buffers are used for fermentation. I thought it was funny because when I found this example online, they had a picture with it and it said buffers used for fermentation. And the picture they had was like a bunch of mixed drinks, which means that whoever put that picture there doesn't realize the difference between fermentation and distillation, which means they probably don't make their own cider or whatever. But alcohol that comes like vodka, rum, all those sorts of things, those are distilled spirits. They are distilled. It's a totally different process than fermentation to make beer. So beer and like the hard cider that Jason makes. So buffers are used for fermentation, which is a process making alcohol. They are placed in before fermentation to make sure the solution isn't too acidic. If the solution were too acidic, what might happen?
Death.
What's in, what do you use in fermentation? What, yeah, well, that's one thing, huh?
Wheat.
Yep. What else do you put in? Okay, so we make, yeast.
Death of the yeast.
Yeah, so when we make cider, we don't put much of anything in it except the yeast. So sometimes we add a little sugar, but not much. But you add the yeast and the yeast munches up all the sugar, right? And when it munches up the sugar,
and it's too acidic of an environment can kill you.
yeah, then you wouldn't have any fermentation. Exactly. But when the yeast munches up all the sugar, it produces alcohol and then gas. That's how you get the fizziness, right?
Well, that's by adding CO2.
No, we add CO2 under pressure to make it fizzier. But when we first add it, we put it down in the basement, and you'll be thankful we do that because it stinks. Because the yeast, you know, if you put yeast in bread, it expels gas when it eats sugar. That's how you get your bread to rise.
Yeah.
But with the cider that we make, it sits in a big bucket and there's an airlock on the top, which is sort of like a weird, like an S on its side.
Yeah.
And you put water in it. And so when the gas comes up from the bucket, the bubble has to move through the airlock and out, which means that stuff isn't falling into the cider because the water keeps it safe. But it does that all the time. Bloop, bloop. And every time it does it, it spits out more gas and it smells. So it smells a little weird. So also you've got buffers in your shampoo and they balance out the alkalinity that would usually burn your scalp. Thank goodness for buffers. And citric acid, and you see citric acid and sodium hydroxide. They're two examples of buffers used for shampoo. Citric acid is in like everything, right? This is one of the reasons it's in everything. Yep. And then here's another example. So baby lotion is buffered to a slightly acidic pH of 6, which inhibits the growth of bacteria and other pathogens. So think about that. That makes perfect sense, right? If you put something slightly acidic on your baby's skin and it is preventing the growth of bacteria or maybe some fungus and things like that that you're trying to keep off the baby's skin, it's helpful.
So is citric acid, what's the pH of citric acid?
I do not know. That's a good question.
If it's so common, then it's obviously not like 3.
It is. It's pretty
You could ask
high.
the spy.
I know, but she's probably going to give me something stupid like she did the other day when I asked her some simple question. It is between 3 and 6.
6.
Wow, 23.
Yep. So that's got to be like super acidic citric acid.
Anyone ever I've done this before. Have you ever read the ingredients?
Wow.
Back at the Doritos?
There's a question.
It's crazy.
Yeah, you ever see that? You know, when you look up something, there's usually like the Quora type questions.
Yeah.
Someone actually asked, is citric acid acidic or alkaline?
Wow.
Citric acid. I love people Oh.
The first acid is a base,
All right, so why, this one was in your homework, I believe. Why is the steepness of titration curve helpful in locating the equivalence point? Michael knows why, Michael.
Because then you have less flow in between the two, right?
Yeah.
It's either nice. You tapped my pen.
Yeah. Your
It's-
titration curve implies that the pH changes very rapidly near
Yeah.
the endpoint, so precise volume can be measured.
If it was,
It's steepness.
no.
What have we got? Go ahead.
Oh, okay. Its steepness is helpful because if it were any less steep, you would need a more exact way of measuring.
Yeah, okay. All right.
Makes it very
The less,
obvious.
yeah.
Mm-hmm.
Because
So
it's
did
steep,
anybody
it's
get
either
this one? I was just
red,
curious. Oh,
blue,
sorry.
Or like right.
Right.
Yeah.
So I was just curious with this one. I tossed it in there to see what anybody got. Did anybody get these? The 3 Ka expressions?
Yeah, we looked them up.
Yeah, did you look them up?
Yeah.
Okay.
No.
Yeah, that's I think what a lot of people would have done.
A1,
I just thought I'd do
Yeah, I was just curious to see how you got it. Yeah.
Well, I did not get
And then this one has the smallest value. Now that one you should be able to determine the value, which is
Yeah.
the smallest value based on, you know, how small your answers, how small your number is going to be in the end.
It's not what we have. We have the number version instead of the written.
Oh, you have the number version. Okay, all right,
Yeah,
same
I
thing. How did you get a number version if you didn't know the molarity? Well,
Yeah, the
right.
first one is 7.3 times 10 to the negative 3, and then 6.3 times 10 to the negative 8, and the last one is 4.8 times 10 to the negative 13.
Yeah, okay. I was just throwing it in there to see if anybody was going to try something funky or if y'all just looking it up. So here is how you should be able to get it if you're going to get it yourself. I found a bunch of nice little short videos for this week. I like that when they're little short.
We'll talk about what happens when we put phosphoric acid with water, so H3PO4 in water. Phosphoric acid, H3PO4, has this H in front that tells us that it's an acid. In fact, there are 3 acids, and each one of those is going to come off. So we'll have H3PO4, we'll lose 1 of those H pluses, and then we'll have H2PO4. PO4. So let's talk about how this happens.
Wait, I think y'all missed that part. Hang on. This is the most, this is the part where it explains it.
H3PO4, there's this H in front that tells us that it's an acid. In fact, there are 3 acids, and each one of those is going to come off. So we'll have H3PO4, we'll lose 1 of those H pluses, and then we'll have H2PO4. We'll lose that, and we'll just have HPO4. So let's talk about
See that?
how this happens.
Yeah.
There you go.
First of all, we need to recognize H3PO4 as a weak acid. This is just something you need to memorize. So here's a table with strong acids, strong bases, weak acid, and weak bases. We don't see H3PO4 on the strong acid, so it must be a weak acid. Here it is right here. Because it's a weak acid, that means it's not going to break apart or dissociate completely into its ions. So if we look at our equations again here, we see this equilibrium symbol here. We don't have that straight arrow. So H3PO4 will add into water, it'll lose this H plus and have H2PO4, but some of this is going back to H3PO4, so it's an equilibrium. For the H3PO4, it loses that first H plus. That's the easiest one to lose. Losing this other one here from the H2PO4, that is more difficult. And finally, for this HPO4, 2 minus, when it loses this H plus here, this one, that's the most difficult one for it to lose. We should write aqueous after each one of these ions because they're dissolved in this water. Little AQ after the
It's so
H
tiny.
plus here. And I won't write it for all of these, but all of these ions, they're going to be aqueous. We should also note that this H plus is aqueous. It's in this water here. So what happens is the H plus joins with the water molecule to form H3O plus.
There's your hydronium
Sometimes
again.
you'll see this written instead of H plus, H3O plus. It's the same thing. We consider them to be equal. So to recap, H3PO4 is a weak acid. Because it's a weak acid, it won't dissociate completely. But if we have some H3PO4 in water, some of it will change into H plus and H2PO4 minus. Some of this will lose a hydrogen to form this HPO4 2 minus, and some of this will lose its last hydrogen to be PO4 3 minus, the phosphate ion. All of these are happening at the same time, and we have these different equilibriums set up. This is Dr. B
There you go.
discussing what happens when we put H3PO4 plus H2O.
So I didn't want you, I don't want you guys to have to, I'm not gonna hold you responsible for doing one of those, but I wanted you to understand the idea behind it, which I think makes sense when you see him work through it. You lose one hydrogen, you lose a second. Obviously, it's gonna be easiest to lose the first. So who has this answer? In preparing for hydration, cleaning
Well, I
your,
have it, it's just over there.
yeah, it's over there. Who remembers it?
I think this one.
It's just make sure there's, because if there's residue or anything, it just mess with your equation.
Right, and the
Yeah,
bubbles mess
yeah.
with it, all that business,
It
right?
just
We talked
gets-
about
It just
that.
gives you a less exact answer,
Right.
that's all.
Yep, no contaminants and air bubbles mess up your reading, which we talked
I
about.
think we have the answer for the last one, not the first.
Okay,
Yeah.
what do you have?
Ka equals 0.30, 0.000812.
Okay, all right. I can't remember the number. So let's look. So this was the answer. 1.6 times 10 to the negative 4. So how did we, good God.
Take that out.
Y'all okay with
Take that out there. The shoes are.
Shoes are falling
Well,
out.
actually,
What?
So here's how we get it. Here we are with our 0.025 molar. And yep. All right. So, all right. Got the dog. All right. So basically, you got vinegar, aqueous, and formic acid, not vinegar. So you got your formic acid and your water. Breaks down into your hydronium.
So, yeah, we kind of did correct.
Okay, kind of close.
yeah, we used, there was a pretty helpful thing in here.
So in your equation, if you're,
Yeah. We did think this, we just didn't know why.
there you go. Okay. So if your, what's the word I want? Coefficients are 1 to 1,
Yeah,
right? Then you know that they're in equal amounts,
okay,
that this ion and this ion are
Okay.
going to be in equal
Yeah.
amounts to this ion and this ion, right? And then you divide it by the whole. So it's basically part. So there's your part and your part. They're the same because the coefficients are the same. Divided by the whole,
I did my work on a separate page, so I don't have that page.
which, whoop, I'll go
But
back one, which puts you right here.
yeah. I think we did the calculations wrong, Cole, but we got the.
I don't think I put one of these on your test because that would be difficult
here
to,
it is. Yeah,
Type
this is
in.
what we use.
yeah, there you go. Good.
We use
Yeah.
this crap.
Okay.
A dog.
And it had the same 1.82 for us. See, Ka of acid is there, 1.82.
Yeah, Cole, we just did the calculations wrong.
Do we?
Yeah.
Okay. But you got the idea. There you go.
So this is H2O3.
All right. So Miss Jackie is going to be ready for her class in about 7 minutes. Before
We did that.
we move on
We
for
did the
that,
calculations wrong.
just real quick, I want to make sure you guys see what is coming. I know we always kind of go over stuff. You do have a test this week.
Yeah, how is Spanish working for?
And she's gonna live stream right
For
here.
you too.
Yeah, I'm at 2:30.
All right, so real quick, here we are today, right? Next week we have, ta-da, last of the quarter. Last lesson of the quarter is next week. Yep, and then we go
Next quarter, we get new lab groups.
Q4, you do get new lab groups.
Aw.
Yep,
Aw.
No, it's not you, it's the other two.
and that's fun. All right,
I have to prevent you
so then when Q4 starts, we're gonna move into our,
saying it's fine.
listen. Q4 is going to do, we'll be out of all of this stuff like acids, bases, solutions. We're gonna touch on redox reactions, then we're gonna move into nuclear chem and just touch nuclear chem pretty lightly. And then it's gonna be carbon and organic and biological chemistry very briefly, which again will lead us nicely into bio. Next week, I will be handing you your Q4 packets.
Okay.
So you will get them. Yours is done. I'm finishing the juniors. And there will be one lab coming up. It is 27, I think. It might be,
27 is
27. No, it's either 27 or 28.
So 2 or 3 weeks from now.
Yeah, it says it clearly on the first page of your assignment in your notes. It says it very clearly. You need to come to this lab. No, it's not. It's later. It's like 31, actually. It's way later. But it says you need to come with, if you have an internet capable device, specifically a tablet or a laptop, bring it that day. It's going to be a WebQuest style lab for our nuclear chemistry unit. So
Okay.
that way we can do something a little different.
Yeah.
All right, I'm gonna let Shannon go. Bye, Shannon.
Bye,
I'm gonna
Shannon.
get set up
Oh, do we need
for.
Do you have a review for the test?
Do you have a review for the test? All right, hang on, Shannon. Don't leave yet. 5 minutes we have.
Do a screen share.
Yeah.
Yeah, I'm
Or
gonna
actually
take.
do
I'm
screen
gonna
share.
take my
Never mind.
screen share
Oh,
off.
you got a whole bunch of birds out there.
I always have birds out there. I'm gonna stop my screen share. There we go.
Let the dog out.
He doesn't care about the birds. He only cares about the little four-legged thing that shows up out there sometimes. You know that I'm talking about? The little gray ones with the bushy tails. He cares about that.
You
He
said
knows the
that's why
name.
he'll bolt out there.
Like, what now?
He knows the name of them.
Oh yeah.
That's awesome.
You know, because if there were a squirrel outside, a squirrel would be at the bird feeder, and a squirrel would eat all that bird
Ozzy
seed.
squirrel.
Is there a squirrel, Ozzy? Can you go check? Thank you. Yeah, it's pretty sad. All right, really quickly, because I can't cut into Miss Jackie's time, so I have 4 minutes.
Yeah, please.
If you really want me to tell you what to look over. And look at you, screen share is still up, and I don't know why, because I told it to stop. Hold on.
Oh, no, here he
I
comes.
can't let that up. Wait. Why is it doing that? Told it to go away.
So I don't think it's screen sharing. I think it's just you have it.
No,
on-
it's still, yeah, I know, but I still should be able to.
You have it on TV. You're not sharing screen.
Yeah,
You're
yeah,
showing it
yeah,
on
yeah,
TV.
I know. I don't want to turn that off though, because it's a pain. I will though. I will though.
I think it's kind of your only option. What the heck was that?
Bro.
You can be the
Disappear
best
there.
animator
God.
Ever, my God. Are you a voice actor?
All
Say
right.
welcome to God.
Spider-Man movies?
Did it not disappear yet? What the heck? Oh, there we go. All right, so then, all right, you're gonna need to know. Define, you're gonna be able to define equilibrium.
We good?
Mm-hmm. You are going to need to understand what acids do, like how to describe an acid. Not is it bitter or whatever, but it donates protons, it reacts with metals, that kind of stuff. It conducts electricity well.
Do you need to know like different characteristics of it, or just the one thing? About
If you can identify one that doesn't belong, you'll be good.
it? Okay.
What generates hydroxide ions?
Bases?
Yes.
Acids and bases. Yeah.
No,
Oh,
bases,
yeah, bases,
hydroxides,
it's just
bases. Yep. What do you call something that can react as both an acid and a base?
There's a really fancy word for it.
Yep, starts with an A.
Oh.
Amphoteric. Could you recognize it amongst some other choices?
Probably.
Good. So remember that Bronsted Lowry, they defined acid base, they defined acid base reactions by saying that acids accept protons and let me see, how do I phrase this? I was reading it wrong.
It's just about
Conjugate acids and conjugate bases. Yeah, I can see both answers and other things on my screen, so I'm trying to see how it's, the way the setup's a little weird. So what's pH and what's POH? Specifically, what are they measuring?
Well, pH measures how much hydrogen.
Yep. So what's
and
POH?
measures how much hydroxide.
Hydroxide. Yep. All right.
Yes.
Oh, it's ball.
Understand your equivalence point and end point. Be able to describe the purpose of a buffer. And the homework question about burets. Be able to maybe rephrase that answer. Okay, now I gotta get Jackie up for you guys. If you want to take like 2 seconds, do it quickly. 'Cause she's coming, so
Cool. Your class starts at 2:30.
I don't know what he's doing with her.
I'm staying till 2:30.
Yeah, I know you're staying.
How's it come? Come here. How's it come? Come here, come on, come on, come on. Let's go. Ready? How's it come? Ready?